In this unit, we discussed a language for describing experiments and their outcomes, as well as several rules that help us quantify the likelihood that those outcomes, or a combination of outcomes, occur. A particularly useful visualization technique is the Venn diagram, which helps us depict the sample space of possible collectively exhaustive outcomes of an experiment and some specific events of interest. We use the Venn diagram to help motivate intersections and unions of events. The intersection of events A and B suggests that both A and B have to both occur as a result of our experiment. Intersection implies and. The intersection is represented with the overlap of events A and B on the Venn diagram. If there is no overlap of events A and B, then those events are said to be mutually exclusive of each other. The union of events A and B suggests that either A or B could result from our experiment. Union implies or. On the Venn diagram, A union B is represented with the circles A and B, including their overlap, being shaded. Also, the complement of event A includes every event in the sample space that's not A. With respect to probability, we said that there were three primary views of probability that describe different situations. The first is classical probability, where, to find the probability of A, we know exactly how many ways there are for A to occur from our experiment, and we know exactly how many possible events that could result from our experiment. The ratio of these two numbers is the probability of A. The second view is relative frequency, where, to find the probability of A, we go back in history and count the number of times we saw A occur in an experiment, and we count the total number of outcomes we saw from that experiment. The ratio of these two numbers gives us an idea of how likely A is to occur. The third view of probability is subjective probability, where we use several sources, maybe some history, maybe some intuition, maybe some extra information, to draw conclusions about the likelihood that event A occurs. There are two properties of these events that must hold. The first is the probability of any event must be between 0 and 1, inclusive of 0 and 1. And the second is that the sum of the probabilities of the individual mutually exclusive events that make up the sample space must be 1. These two properties help establish some rules. For example, naturally, A and A complement are mutually exclusive and collectively exhaustive. Therefore, the probability of A plus the probability of A complement equals 1. Knowing the probability of A helps us find the probability of A complement. Probability of A is referred to as a marginal probability, the probability of an event without any consideration of other events. A conditional probability for events A and B is the probability of A given B, or the probability that A occurs given that we know that B occurs. The probability of a union of events, the probability of A union B, is calculated as the probability of A plus the probability of B minus the probability of A intersect B. We subtract off the overlap that we counted twice when adding the probability of A and the probability of B. This is called the addition rule. The probability of an intersection of events, the probability of A intersect B, is calculated as the probability of A given B times the probability of B, or the multiplication rule. The logic of the multiplication rule is typically used to calculate a conditional probability when the intersection is known. The probability of A given B is equal to the probability of A intersect B divided by the probability of B. We also saw that the probability of A can be calculated as the sum of the probabilities of the intersection of A with all mutually exclusive and collectively exhaustive events in the sample space. Given the consequence of the multiplication rule, this marginal probability can be written as a sum of conditional and marginal probabilities multiplied together. Finally, Bayes' theorem is another result of the multiplication rule. We use Bayes' theorem to calculate a conditional probability that we can't witness, but we can witness the inverse conditional probability. The key to all probability problems is to first define any events and the probabilities of those events that are known. Then determine how to implement rules to find the probabilities that you don't know.